Yeah, so that's me. I work at QuestDB. I know you probably don't know QuestDB. That's fine. We are an open source time series database. And I'm not going to be speaking today about what you can do with QuestDB and so on. I'm going to be speaking about what we did to make it perform better. The number I have there, 6 times faster, it's just a number. It's not random, but in the past 2 years or something, we made the engine to be significantly faster for some type of queries. I will tell you more about that in one moment. So 6 times, it's a number we have seen some benchmark, but actually some queries are hundreds of times faster than before. Some queries are pretty much the same. They didn't change at all. So today I'm going to tell you about the journey of why we wanted to make the database more performant and the kind of things we did internally to make it work better. And the first thing, if I was listening to this talk, I would probably, especially me from the past, I would be a bit surprised about 6 times faster, because typically when you're using a database, the database doesn't get 6 times faster from one year to the next. It gets always a bit better, they get new features, it gets a bit faster, but databases are known to be, or used to be known to be, the weakest point in many projects. I started doing development professionally a long time ago, and at the time I was a backend developer, end of the 90s, all the 2000s. Every time something was slow, it was the database. Like, oh, something is broken is DNS, something is slow is the database, and that's about it. But in our case, for QuestDB, speed is part of what we sell. Some databases sell you a lot of functionalities. We have some interesting features, but actually QuestDB is specialized on time series data, in data which is moving very fast. QuestDB is used to power dashboards like, I don't know, this is, for example, a real live dashboard refreshing 4 times a second. Doesn't sound like much. I don't know what is there. Yeah, so it refreshes every 250 milliseconds. Doesn't sound like much, but a main use case for QuestDB, apart from other use cases we have like in energy or aerospace, but the main use case is on finance. And on finance, some data, market data, tends to come fast. For example, the Standard & Poor's Future Index, in a typical day, it can get about 700, 800 million records for one day. If that day Donald Trump is doing something with tariffs, you can get to 1 billion records, because it's like markets get crazy and so on. And in reality, it's not that bad. At any given second, you are ingesting maybe 10,000, 15,000 events per second, but at peak, you can be ingesting 250,000 events per second, and you still want your dashboards to refresh in real time as much as you want with that kind of data. So when you are running a database which is for analytics, for fast analytics, being fast is actually interesting. And before I continue speaking about what we did, time series is different to other types of data, because people are mostly interested in what happened recently. So you are interested in the historical data, but it's very important that you are very low latency and very fast to ingest the data and to query the data as fast as you can. So you can also query historical data. You can downsample. You can do whatever you want. But the recent part of data, being fast there, is quite important. We are an open source database, Apache 2.0 license. And we specialize on very fast ingestion. The engine is built mostly in Java for historical reasons. Always people asking me, why Java? After the talk, maybe you can ask me. But it's mostly in Java with 10% of C++ and lately some Rust. But the Java we use is a bit uncommon, because since we care about performance, we cannot depend on the garbage collector randomly appearing. So we manage memory natively, manually. So we cannot use anything that operates on the heap, basically. So we have to implement our own version of the standard library for pretty much everything. For, I don't know, input, output, network, data types, string functions, whatever. So everything is built from scratch, pretty much. That's basically the thing. The first thing people, when start contributing to QuestDB, the first thing they tell us is that our Java code look like C++ code, and the C++ code look like assembly code. And that's about it. That's kind of the thing. So we are very, very low level for making this perform well. And you query QuestDB with SQL. And these are some of the extensions we have for SQL. For example, this here at the top This query here is using this pattern, which is telling me, filter everything which happened on the 13th of June 2016, and 1 month afterwards, and in the next 3 years. So it's like quite like expressive. For doing these queries, you could do with other database, but we specialize on time. So we have these extensions for making working with time a bit nicer. Or this one, for example, is telling me, select wherever, do a sum, but instead of a group by, have a sample by. So basically here, for its different symbol and its different site, I will have an entry every minute. And if for one particular minute I don't have any data, I will have like null values. I could have a linear interpolation. I could have whatever. So you get the idea. A few interesting things that we have, but that's about it. Or what is the latest value? Here, the latest one is like, tell me for its different symbol, for the different value of its symbol, which was the latest row. Imagine you have some data and some symbols are ingesting several times every second, others only a couple of times per minute. I want the latest row for its symbol. So again, you want to do that on another database, you can do it with window functions, simple enough, but it's a bit more expressive. That's kind of the idea. I don't want to bore you with these things. I'm not going to skip in this. So we are pretty fast. We've been pretty fast from the beginning because that's our value proposition. We are very fast. But we were very fast until 2 years ago, only for time series queries. That is, for queries in which you have a filter by time. Everything we have on the database, we have a lot of optimisations to be super fast in things that are filtered by time. We store the data always partition. You can define the granularity, but it's always partition by timestamp. It's also sorted by timestamp. We don't use indexes. So basically, the timestamp, let's say, is the index. And whenever data is coming out of order, we need to rewrite a lot of things. But then when you do a query, since typically on time series you want to query a continuous slice of time or several continuous slices of time, we can just position at the beginning of the interval, read sequentially. It's very fast to do that, like when you are doing that. So queries that you want to downsample data, filter by time, we were super fast from the very beginning in many benchmarks. For other type of queries that were not about time, we were not super fast. We were faster than a Postgres, but we were slower than many other analytical databases. And we were fine with that, because we don't want to solve every troller in the world. We want to solve the troller of time series data. But our users were telling us, I have QuestDB already. We like them. It's fast. But once in a while, I need to do other queries that are not time-based. And for that, you suck. Like, OK, kind of. I mean, we didn't really suck, but you know what I mean. And we wanted to solve that. We wanted to say, OK, we want to still focus on time series, but let's see if we can improve the database to be a bit better. So we started looking what other databases were doing. The cool thing about open source is that you can check what everybody else is doing. And we saw, hey, most databases that people like, analytical databases, they speak SQL. It's a good thing because we already speak SQL. Most databases that are fast, they have the columnar storage format. We had already a columnar storage format. That's cool. Most databases try to use all the resources. Some databases, like more conventional databases, transactional databases, they run every query on one CPU. In our case, and in many other databases, you try to parallelize as much as possible all the hardware that you have. We're doing that. And they are doing group buys and join buys and blah, blah, over things that are not necessarily accessed over time. That was the thing that was the only thing that we saw that was different to what we were doing. So we started thinking, what can we do to make those queries perform well in a model in which we store the data partition by timestamp, sorted by timestamp, so we have the trade-offs. How can we make this better? And the first thing before you start improving performance, you need to know which is your baseline. So we took a look at some benchmarks in the industry to see how we could measure what we were doing. We were already using TSBS. It's a specialized benchmark for time series. And in that one, we were pretty cool. But it was for time series. It's open source. You can, it's not really super maintained. I mean, it used to be maintained by Influx at the beginning, then by Timescale, and now we maintain it, but we are the maintainers, so it seems biased. I mean, we try not to be, but that's the thing. But that's for time series, so we were not interested on that one. TPS is a classical benchmark. It's too classical for our liking. The shape of the queries don't really look like the queries people do in the systems where we operate. DB benchmarks by DuckDB, it's interesting. Everything with DuckDB is always cool. but it was not really specialized on real time. And then we found ClickBench at the time. ClickBench is a benchmark by ClickHouse, in which they perform pretty well, but other databases perform better, which is good. It was created in 2022. The data set where they run the benchmark is a single table, so it doesn't really look like production for some of the systems, but still, on time series, very often you have a single table. The table is not huge. It's only 100 million rows, which is not very big, but it has 100 columns, which is already interesting because the type of market data I told you before, where you are ingesting hundreds of millions of records every day, they typically have 5 to 10 columns. The symbol, the market venue, the price, the timestamp, blah, blah, blah. So in this case, 100 columns, 100 million rows is not huge, but it's big enough. I believe the uncompressed CSV is around 80 gigabytes of data, so it's not that bad, but it's still good enough for benchmarks. So it's quite popular for analytical databases, and the way it works, they have 43 SQL queries, and you have to run the 43 queries, and you get a score based on how you perform on those queries. And some queries are very simple. Just like, give me everything, give me account from the table without any filters, give me account with everything that doesn't match this. Some queries are just fabricated because, give me the user ID from a table where the user ID is this one already. I know the user ID. I'm selecting the user ID. I understand you want to benchmark this because whatever, but some queries are actually quite interesting. They have some conditions, so a lot of aggregations, order by, limit. Those things are slow for a database. Doing an order by, having to apply a limit after sorting, it makes things slow. That's kind of interesting. And some queries are proper analytical queries, like this one. So it's like, give me the sum of one column plus whatever many times. I believe it's like about 90 times in this column. So, some queries are pretty cool. That's how it works. So what we did at the time was, OK, let's go into run this on QuestDB and see how we perform. Oh, boy, was not great. We are here, somewhere here, QuestDB. And at the time, we're performing 33 times slower than the ideal database. 33 times slower was not, it was like, I don't know, we knew we wouldn't be super fast in queries that are not time series, but, it was like too bad. By the way, you check the number one, this was in October 2022. You look at the first one that at the time was ClickHouse, the creators of the benchmark, makes sense. So when you look at the first, they are not 1, they are 1.3. Because the way these benchmarks work, which is pretty cool, you run the 43 queries, and a machine that will be the top machine, the top performing in all of the queries, will get the score 1. But there is no engine, which is the fastest for all the queries. So ClickHouse is faster, in this particular version, is faster than everybody else in most of the queries, but in some queries it's not the faster. That's why the top is not. So this doesn't mean we were 33 times slower than ClickHouse, but we were sensibly slower than other people. So we started doing things, and about a year later, we were already not that bad. Hey, QuestDB, it's only 15 times slower. It sounds bad, I know, but it's half as slow as the year before compared to other databases. And of course, everybody else was improving also performance. Again, a year later, and we are already starting to, this was like September last year, and we were already not that bad. We are already at 3 point something slower than the ideal machine, which is not ClickHouse anymore, and which is 1.5. Actually, ClickHouse here, I'm mentioning ClickHouse not because of anything. I love ClickHouse. It's a super cool database. If it solves your case, use it. I'm just mentioning ClickHouse because they did the benchmark, so they have some say here. But I don't have anything against that. They're pretty cool, just in case I'm sounding, because I don't want to sound unfair or anything else. Okay? So they were like, we were already only 3 times slower. And actually, this year, we were like, again, a bit faster, like 3 times only slower than the top. The top was 1.5. ClickHouse was 2.3. So we are already like, in a place, and when you filter only for the same type of machine, we are in the top 10. Actually, if you go today to ClickHouse, I believe we are in the top 10 of databases to the benchmark. this is the live version. Yeah, this is the live version of the benchmark. And we are here. It's like, we are, I believe, in the top 10. You can see here some repetitions because some databases, they run the benchmark with different configuration, optimized for memory, optimized for whatever. But in terms of engines, we're in the top 10. So after everything we did, we are still not the fastest database. Other databases are faster than we are for analytical queries, but we still are very fast for time series. And now we perform fairly well for other analytical queries. So that's the thing. And the talk here is what we did to make this work. That's kind of the idea. A long intro, but hopefully it made sense. So, So it took us about over 2 years. We are not a big team. We are open source, so we have like 100-something contributors. The core team is a bit smaller than that. So it took us over 2 years, but of course we're adding other features in the meantime. So basically, this thing about improving performance was not a main project. It's more like something on the side. It's like, hey, can we do something to perform better? OK, since we are doing this, let's go to change this and that. So we're adding new features, and in the meantime, revamping a few things, blah, 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 blah. We tried some things that made the database slower, so we didn't we didn't release those things. So we tried many things, and I'm going to tell about some things that work for us. Some things were very simple. We optimize in the database as much as we can, but in the end, there is the time is finite, so you cannot do anything you want to do. So some functions we optimize only for some data types. We try to parallelize, we try to do many things, but for example, in the data set, you have a query like this, which is a count distinct by user ID, and user ID here was an integer, and we didn't have parallelization for that type of query. So what QuestDB was doing internally, it was converting from an integer to a different data type, and then running the count. So it was slow. So what we did is like in many functions, we added support for other data types, so we don't have to do type conversions. So some things were very straightforward. In some, for example, count distinct for some data types is still not parallelized. But those data types, no one is using that. So you typically don't do a count distinct on a float number. Doesn't make sense. So we don't optimize for that. Okay? So you run some queries, you will see it doesn't parallelize, but we're doing like some simple things. Then there was something a bit more interesting. In QuestDB, we had, from the very beginning, a just-in-time compiler. The way it works, we take the query you have, and we try to compile to machine code the filters in the where and some aggregations. We try as much as possible. So what we are doing here, basically, we have from Java, with GNI, we call the C++ engine. Since we are doing direct memory mapping, we don't have to convert data types. We use the same formatting memory between Java, C++, Rust, and the file system. So basically, we only have to pass the pointer from Java to the C++ function, and then the C++ function is giving us the pointer back where we have to read the data. It's pretty fast, the switch over. But the thing with our compiler, it emits machine code for doing SIMG. Basically, with one operation, you are going to affect several memory registers. That's the idea. So it was working from the beginning, but it was working only for some specific use cases. It wasn't working for many scenarios because we had implemented only a few parts. The way it works, the just-in-time engine, you get the SQL query, we take the predicate we convert to an AST, to a syntax tree. The syntax tree we convert to an internal representation. Is similar to the bit code you get in an LLVM or whatever. So we have an internal representation, and from there we convert to machine code directly to be executed. So you have a filter where you have any condition where this number is 10, and then you want to sum. The filter and the sum can be executed directly on machine code on the processor, and we do this using AST-JIT, which is SMJIT, which is a library faster than LLVM. And this is basically what it looks like. From Java, we just call our engine, and we say, this is the address of the function that you are going to execute. This is the pointer where you have the columns. This is the pointer where I want to get the results back, and so on and so forth. So what we did with this compiler that we already have, I told you earlier that our C++ code looks as assembly. This is C++, but as you can see here, I'm accessing directly some memory registers directly. So this is the C++ for the engine, for part of the engine. But for each operation we want to parallelize, we have to write something like this. In this case, this is the filter to compare if two double are equal. So for each operation you want to parallelize, you need to write the function to parallelize that, to aggregate or to filter. So we had to add a bunch of new functions to do this. For example, in the past, this query wouldn't run in parallel because we didn't have the filter for strings to be not null. So everything else was parallelized, but this particular query, which is in ClickBench, it was slow because it couldn't use JIT. So yeah, we added the is not null operator, and again, it went faster. That's, that's a bit the things that we went doing. Actually, I think this query, so I can show you something. I'm going to execute this one. So I started before we started the talk. I started 3 different instances of QuestDB. I have one which is fairly old. This is QuestDB of 2.5 years ago. So if I run this, actually this was quite fast. It took only 500 milliseconds. And this is QuestDB as of today. And yeah, sometimes the call run, it takes longer because it has to go to disk, but second time data is already mapped in memory. So we don't cache the results, but we cache the content that we leave to memory. So you can see it's 100 milliseconds, which is about like 4 times faster, 3 and something faster than in the past. So we have like those things that were like improving the engine little by little. And then we do like some things. For example, when we see something like a count distinct that we had before, now that we have some functions that we parallelize, we rewrite this query. Count distinct is not something we had parallelized, but we had the functions to do a count and a group by. And a count and a group by is the same as a count distinct. So rather than in some cases writing a new function, what we do is like rewrite the query to something equivalent that already has the functions, which is faster because you don't have to debug the function twice, and you don't have to, if you change something, you change only in one place. So we have a lot of rewrites on the query engine. Wherever you run a query, the query planner needs to check how it's going to execute. We never cache results because we are a fast database, so caching data doesn't make sense often, but we cache the query plan. So every time we get the query and we convert to the machine code, as I told you before, we cache the query plan in the connection. So you run the query again. We don't have to recalculate or rewrite or whatever, but we do a lot of those things. A lot of rewriting things into joins, into group bys, into different aggregates. So we are going to be using the filters we already have parallelized. That's basically the idea. You still with me here? Cool. Then we did some things that we like reading a lot about what other people are doing. And we found someone on LinkedIn saying, hey, it's very cool that you can do things like SWAR is like SIMD, but over normal registers. So basically, in SIMD, what you do is like you take an instruction and you execute in parallel over multiple registries. So SWAR, basically what you do is you do the same, but with regular memory, for saying so. So in this case, we saw someone that was saying, if you have a search pattern like this, which is very common, you want to find something that looks like it starts with or looks like something, and it's a short one, rather than having to compare character, sorry, I was worrying. Sorry, rather than having to compare character by character if the characters match, it's how you will implement. What you can do here is you can compare in parallel each of the characters. So if the string you are looking for, it fits on a registry, you can just put the characters in different bits of the registry one after the other and apply the search in parallel. So you are speeding up quite a bit. It doesn't look like much, but when you are scanning a billion rows in one query, everything adds up, and it gets quite faster. So we have a lot of these low-level optimizations. If the string is longer than what it fits in a register, what you are looking for, we cannot apply that. But if it fits, then we go to this plan. And these small things, which are not, to tell you the truth, when you are working with market data, you typically don't look for looks like. You search for the exact symbol you are looking for. But if you want to run this, now it executes very fast. So those things were quite interesting. Same things with record replace. Regular expressions, we noticed were not very fast in our implementation. And we had an engine in Java. And we said, hey, we are going to move the engine to C++. It will be faster. So we went, we researched a little bit. We found the usual suspect, what they were doing with C++. And we found a pretty cool, pretty fast library. We tested that one. And we found out, actually, that it was not really much faster than the one we had in Java. But the problem with the one we had in Java was that it was using a lot of garbage collection. We tried to avoid that, but that one in particular, at some points, it was collecting data. We tried to avoid that in the hot path. So basically, we changed the implementation to avoid garbage collection. And with that, in Java, we actually were faster than in C++. But it sounds like not really that intuitive, but sometimes it happens. So it was also interesting for us to try, to test. So these things that sounds like simple stuff, in the end, it's a lot of tinkering, and it's like pretty fun. But you find interesting things here and there. In QuestDB, we store data by columns, as any other analytical database. So when the columns, we have data types of different types. Some data types are fixed size, and some have variable size. When you have a fixed size, like an integer or a long or whatever, storing the data is straightforward. You have the binary file, you store one integer after the other, and then if you want to go to the row 200, you know the offset, because they all have the same length. Pretty simple stuff, sorry. But when you have variable size, with strings, for example, that's not the case. So with strings, we were keeping two files, one with the offsets and the other with the strings. The strings actually, until a year ago or so, they were UTF-16 because of Java legacy. And UTF-16, as you can imagine, is not ideal because you are wasting a lot of storage just for storing strings in memory and on disk. But yeah, it was UTF-16 at the time. And the strings were like this. At the beginning, we were storing the size. Then we were storing all the binary characters. And then the next string. So we need to keep an offset file and a content file. And that sounds straightforward. It's what you will do. But it's a lot of pointer chasing. When you need to find, where are things, a lot of indirection. You have to move to a lot of places. Not ideal. So we decided to go to UTF-8 and also implement the strings in a better way. So I believe DuckDB also have a similar implementation. Some people call this German strings. I don't know exactly. I believe it's because of DuckDB. But yeah, some call it German strings. So yeah, thank you, Germany, for that. So basically, on a German string, we do this slightly different. What we do is we still have two files, but one is not the offset. One is the headers, and all the headers have the same size. So if I want to go to the header of the string 200, I know exactly where I have to go. And the interesting thing is that in the header, you store the length, as we were doing before, also the prefix, because in most cases, what people are going to be searching for is like if a string starts by something. It's unusual to find, or at least in many cases, it's unusual to try to search in the middle. People prefer to start with. So we store the first bytes of the string already in the header. So if you are in the offset and you are doing a start with, you don't have to go to the other file. You already know if it's a start or not. But if the string is small enough, the whole string fits on the header file. So you don't have to move from one to the other. And with this change, it was actually way faster to work with the strings in QuestDB than before. So those things, when they tell you, I remember when I was in university and they told me, how you store strings in C, how you store, and you never care about those things. Well, actually, they make sense 30 years later when you are actually applicating for some things. But in all these aggregations, we notice one thing, and is that many group by operations, even if we were very fast for some functions, group by was still a bit slow. And the thing is, when you implement a group by, the naive way to implement a group by, which is how we had it in the past, would be like this. You want to group by something. So this is your column for user ID, and you want to count by user ID. You hash the user ID column. You store the key on a hash table. So whenever you find a row, if the hash doesn't contain this, you store the entry with count 1. If the hash already contains the value, you increase. That's it. So single thread, and you have everything. If you want to parallelize this, and this was our implementation originally, if you want to parallelize, you just divide in chunks. Like I want to parallelize in 16 CPUs. OK, I divide in 16 groups. I pass one part to every group, and every group is going to do this in parallel. And in the end, I have partial aggregations. I only have to put them together. The problem with this approach is that when you are parallelizing the count, but then you are, again, centralizing aggregation. So you get a group by, which looks like this. First, I separate in different tasks. I do the aggregates and the filtering in parallel, but I have a single thread for merging the results. If you have low cardinality, only a few a small number of different values to group by, that's good enough. But if you have a large number of values to aggregate, that single thread is slow. So what we can do instead, which is what we did after that, if you look at sometimes serious databases, they tell you, if you have high cardinality, your queries are going to be slow. In our case, high cardinality queries are still fast. And it's because we did, one of the things is because we did this. So basically, we wanted to make this merge multi-threaded. And what we did was, OK, in the first step, we still calculate a hash of the key. With the last part of the hash, we calculate a bucket, which is between 0 and 255. So we do the partial counts, not only by key, but also by partition. So that means whenever a worker is aggregating in 256 different partitions. So now you can apply the merge step in parallel up to 256 threads or CPUs. So you have high cardinality. This scales pretty well. And those are some of the things that we were doing to make this be faster. So with this, we found out it performs pretty well for low and high cardinality. And again, it sounds straightforward. But you don't implement it like this from the beginning. And eventually you do it, and it's pretty cool. So nothing I'm talking about here today is super groundbreaking. But those are the incremental things that actually got us to be faster than we were before for different use cases. I'm going to skip this one. And something that is important is that group by and other operations, a lot of aggregates, depend on hashing the data. And hashing the data is trivial. You have an integer. I have an integer. I don't even need to hash. The integer 1 is the bucket 1. Integer 2 is bucket 2. But in real life, you group by different types. Might be strings, might be integers, might be a mix of integers and doubles and strings and whatnot. Might be a UUID. So we found out, again, that depending on the type of data you wanted to aggregate, different strategies for hashing could give you actually much better results. So now we have a lot of specialized hash tables. It's an internal joke in the team, but we have a hash table for everything. If I have a group by with 2 varchars and then an integer in this order, I have a hash table. But if the integer goes in a different order, I might have a different hash table. If the hash table is going to be updating very frequently, we might go with driven hood hashing or with other strategies. So basically, changing the implementation of hash tables, and rather than just using a hash table in Java, creating your library of specialized hash tables, it makes aggregations and filters significantly faster. So those are the low-level things that we do. And with this, I'm going to be finishing fairly soon. I now have 5 minutes. So the last thing I wanted to, because so far, I believe, hopefully I don't have anyone here, but this talk, I already did it a few months ago. And all the content I taught today is exactly what I told earlier. But this part is new. So just because in the past few months, we released, actually one part is still not released. It's in the repository, but not still on a stable release. So the last improvement I want to talk about is the as of join. As of join is a specific type of query. I believe we were, if not the first, one of the first databases implementing as of join. I believe we were the first. Now you have as of join in DuckDB. You have as of join now in ClickHouse. You have as of join in many databases, but we've been around for 10 years, and we have as of join for a long time. So an as of join is a type of query in which for each value in one table, it will give you the value for another table, with the same timestamp or the timestamp which was immediately before. So here, you can see I have multiple events in this table. Some events can be matched into the same event on one table. Some events will not match with anything. Some will match exactly. So as of join is quite interesting to have, for example, here, I have a table with prices, and I have a table with trades. So whenever there is a trade, I want to know what was the closest price in time, the one that was immediately before. It might not be exact. It might be completely different, but no, that's the thing. So here, you notice, for example, with Apple, with the AAPL symbol, the first few rows, they all have the same bid price, 176.47, which is the one from this row here. And that's because the first rows here, they all happen before the second hit that you see here, which is 176.33, which appears here now. So that's as of join, which is quite interesting for many things. And as of join, again, was working fine. In general, you have this kind of data in which timestamps are kind of approximate. But if you have a table in which the table you are joining is much larger than the main table, it was not efficient. Because in order to read this, we need first to go to the data file, read the file in memory, and then start scanning from the timestamp in reverse until you find the closest data point in time to the one you are looking for. So in a large table, having to open the whole file to scan backwards, it can be, for every row, can actually be slow. So what we did, we implemented different strategies that we do automatically, or you can hint with a hint keyword. So what you can do is like force that instead of doing that backward scanning, we do instead a binary search. So in the past, if you have an as of join with any other filter, in this case, we're filtering by timestamp and by symbol. So you filter by anything else. The first step in the past will be we filter by the symbol, then we scan backwards the timestamp. That could be slow. So now first we do a binary search for timestamp, and then we filter back by symbol. And in some cases, that's way, way, way faster than we had before. So we try to apply this automatically, heuristically, depending on the metadata, but you can also force it if you know your query is slow. You can just try with the hint, and then if it's faster, just leave it there. That's kind of the idea. And the last part I wanted to say about as of join is that not all the things that we do are about automatically, like, getting lower performance. Some people were telling me, hey, the as of join is slow because some of my data have timestamps very different to the other table. Imagine your latest price for one symbol is not from a few seconds before, but it's from 2 days before. Probably it's not even relevant. But I still have to scan backwards a lot of data on the table. So we added something new, which is a super simple thing, which we added the keyword tolerance. This is in the repository, but still not on a release. So now you can say, as of join, with this other table, based on whichever keys, but only if the data is not more different than 10 microseconds, 1 hour, 2 weeks, whatever time interval you want. But then, if you have a tolerance of only a timestamp, the moment the engine knows that we are already scanned past that, it's going to abort. So it's, again, way faster. That's the last thing I wanted to tell you. So lessons learned. Well, for being a fast and serious database, it's also interesting to be a fast analytical database. You need to choose your benchmark. Actually, we would probably are going to be changing to another benchmark now, which is based on click-based, but also has joins. So you need to choose your benchmark to know how we are getting better. And as a side effect for being better in this benchmark, we actually made other queries for other users also faster. That's what I have for you today. If you like it, just talk to me later, follow QuestDB, we are open source, start on GitHub, favorites, whatever you want. Yeah, I'm going to be available the whole day. So yeah, thank you.
Thank you. Do we have any questions for Javier? Yes, no? I know we are out of time, but Javier is going to be around and would love to answer your questions. So thank you once again. Let's give him another round of applause, please. Thank you.